Hello, Algebra 3 class. I hope that you're having a good day, and I know that there's probably some of you that are kind of wondering and thinking, and some of you are probably going through all kinds of emotions and things right now as we embark into our second week of doing things from home. So just know that I am praying for you and that I really care about you, and I really wish that we could all be together. But since we can't, just make sure that we're staying connected. Just the fact that you're on here and you're listening means that you definitely have hope, because here you are caring about your future. So I'm very, very proud of you, and I want to encourage you that yes, there is a future. It might not look like what we thought it would look like 3 weeks ago, but there is still a hope. There is still a future. And I'm just waiting to find out and see what God does in that future. So even though here we are ready to take a look at linear and angular speed in Algebra 3, and some of you have some great plans out there ahead of you where you might use it in the future. Like I said, I'm just proud of you, because doing things like this, making sure that you still are going to your classes and doing things, just means that you still have hope. So thank God for that. And I'm thanking God for all of you that are here listening. And for those that are not and obviously aren't hearing my voice, just keep them in prayer as they need to be in prayer. So Jesus, please bless us today and help everybody understand. All right, so here we are with our linear and angular speed. Linear speed would be like how fast something is going if it's just kind of moving around, just like my arrow is, and how fast it's moving. You know that you don't always drive in a straight line, but you know that your speedometer is going to give you some kind of a speed on there. And so that how fast, at least your average of how fast you're going, is called your linear speed, even if it doesn't come out to be in a straight line. In our old way of thinking about things, it's really simply distance divided by time. Okay, S in our book is designated for our distance, and T is designated for our time. So we have our V, which is kind of like a velocity. It's a speed. For those that are in my physics class, you know there's more to velocity, but we'll stick it as V as being your speed, S as being your distance, and T as being how long it takes to have that happen. So we can use that for equations. We're going to have a little pile of equations to use today, and they're going to show up on every slide. But as you're doing your work, I would suggest that you have those equations like right down in front of you. Make kind of your own equation sheet so that as you're practicing, and I can't stress enough how important it is to practice so that you get good at these things and so that you are confident in them. All right, so here we go. We're going to take a look. All right, everybody, you didn't know about that, but my dog decided that he needed to bark, so that's why I hit the pause button. So here we are, right back at it. We need to talk about angular speed. Now, angular speed, you're thinking more along like if you have an old school clock that's going around and you're seeing the clock hand go around and around and around. It's basically how the angle is changing in regards to time. Notice that I've got my, I'm thinking counterclockwise, because we know that when you're looking at the unit circle, we have 0 degree, we have 0, and then we have pi over 2, and then we have pi, and then we have 3 pi over 2, and 2 pi, so round and round and round that we have. I'm thinking about it in terms of radians, and as the thing goes around and we're getting different angles, that angle or whatever it is that's spinning, we have our angular speed, with the Greek letter omega. Okay, omega you think of usually as the uppercase omega, but if you draw like that, you get a lowercase omega. And so that's our Greek letter omega equals theta, which we're used to thinking about over time. Okay, so it's how much the angle is changing over the time period that it's changing in. Now what that leads us to is, like I say, we have a little pile of formulas today. I'll talk about each one and then we'll do a few questions to apply them. Okay, so one of them is for what we call arc length. And if you recall, if you have a circle, okay, an arc would be a piece of the circle. So an arc length would be like how far it is from here to here. Okay, actually if you measured it in a line. You know, at the beginning I was talking about linear speed having to do with, sometimes it can, move all around. We don't always drive in a straight line. But we're going to be looking at it as it applies to the piece of a circle. Okay, so an arc length is the radius r. Okay, so the radius r times theta, which is our angle that it passed through in radians. Okay, so we have this formula, the distance along the circle equals the radius times the number of degrees in the, or not the number of degrees, the number of radians in the angle that was formed as the thing went through there. So you've got the angle theta, you've got the radius r, and you've got the distance s as it goes around that. Okay, our speed, our linear speed. Linear speed is different than angular speed. Okay, we just talked about, right back here, we talked about the angular speed. And the angular speed has to do with how much this is changing with time. Okay, but at the same time, we have things happening linearly. We have a distance that could be measured. Think about a car driving around a circular track, or you're taking a little run or a jog, or something is spinning around and you can think about the distance along the outside of that. Okay, so our linear speed, we already said, is distance divided by time. In this case, it's s divided by t. But another way of thinking about that formula, because s, our distance, our arc length, equals our radius times our number of radians that it passes through, you could sometimes replace s with r theta. And then we see that, wait a minute, here's another replacement. Since we know that the angular speed in radians per second, if you multiply that times the radius, then you also end up getting a speed, a linear speed, how far in how much time. Okay, so all of these different formulas can be used. Like I said, I've got them showing up on every slide. You should have them just handy with you as you go through certain problems. You're not going to, as you take notes, don't rewrite them every time. You've just got your paper on the side that has these formulas. All right, so we're going to suppose that you've got a point P on a circle, and the radius is 10, and ray OP is rotating with an angular speed of pi over 18 radians per second. So what that really, if we're thinking about it, you've got your circle, you're thinking about point P is on the circle, all right, and it's moving along, and the radius is 10 centimeters. And as it's spinning and spinning and spinning, okay, this little window, this little thing will be spinning around and go through pi over 18 every second. Okay. We want to find the angle generated, in other words, how far along it goes in 6 seconds. Okay, we want to find the angle that's generated, how far it went in 6 seconds. So in order to do that, we're just going to think for a minute, and we're going to think, all right, I have my speed, okay, my angular speed, and I have my angle theta over my time, which is 6 seconds. So really, all you have to do is multiply both sides by 6, and you get pi over 3. Now, some of you might have thought of it logically and said, well, wait a minute. If I have this and it's spinning around, and I know that every second it goes pi over 18, yes, of course you'd multiply it by 6. But we also have the formula you can do it with either. So either way, you end up multiplying by 6, and we end up with pi over 3. Don't forget that you can cancel out when you're doing these math problems. All right, so another thing we can find is the distance traveled by P along the circle. All right, so as the circle is going round and round, you've got that length, that arc length. In other words, you're moving along the circle and you want to find how far it goes. So here is our theta, and our theta is the angle that it turned through, but we need to multiply it times our radius in order to find out the distance that it went. S, which is our arc length, equals radius, which we were given as 10 centimeters, times our theta, which we just found, how the angle that was generated. So 10 pi over 3 centimeters. All right, if you had wanted to, you could have multiplied it out, but for simplicity's sake, we're going to do things as close to calculator free as possible. Although, of course, we use it for certain things, but just so that you can know that you can do these problems regardless. Okay. We're going to add a question to it. So if we want to find the linear speed, okay, we're thinking about this linear speed in centimeters per second. So I have a certain centimeters, and I have that certain time. I could take this and I could divide it by time. That would be one way of doing that. You could use any of the equations that you have. The easiest one, though, is going to be V equals R omega, because it's the easiest calculating. Yes, you could divide that out by time, but you can also do this 10 times pi over 18. And that will give you 5/9 when you reduce it, 5/9 pi centimeters per second. And that's how far it would be going, how far it would be going every second as it passes around that circle, and how far the actual travel would be along the edge. All right, so we've got all of these things happening. You can use your formulas for this. Okay, let's think for a minute. If we actually did this as distance divided by time, we'd be dividing by 6, which would also give us 10/18, which would also give us 5/9. It would just be a little harder than using this straight up formula. So all those things, you can do things in multiple ways if you need to. All right. So here we have a problem where you've got a belt that's running a pulley. This is more of a mechanical type of a thing. So anybody who's interested in doing mechanical things, this would apply for this. So you've got a belt that's running around a pulley. Okay, and as it's going around this pulley, it's, the pulley would probably be moving something else, and, a whole series of things. But the belt's running around the pulley, and the pulley has a radius of 6 centimeters, and it's going around there at a rate of 80 revolutions per minute. Okay, so that's faster than 1 per second. What we want to do first is we're going to find the angular speed of the pulley. So we've got a little bit of a logic path to follow on this particular problem, because there's not really, there's no formula here that directly talks to revolutions per minute. Okay, but we need to think about what revolutions mean. Think about, for example, that when something has 1 revolution, that means it goes around that circle 1 time. How many radians is that? Okay, think about it. It goes around the circle, how many radians it is. And you should be coming up with 2 pi, because there's 2 pi radians in each time around the circle. So that means that there are 80 times 2 pi, because there's 80 revolutions, which makes 160 pi radians each minute that it's traveling. So here's our number of radians. In other words, this is our theta. Theta. Each minute. Oh, actually, that's each minute. So this is actually our omega. Okay, so 60 seconds in each minute. Okay, 60 seconds in each minute. So that means that we would have to divide it by 60, because there's 60 seconds in each minute. This tells us how many each minute. Divide it by 60 so that we can find out how many radians every second. And this would be our angular speed in radians per second. We are kind of thinking about it this way. We had to figure out how far it went first, 160 pi. But realizing that it was per minute, we had to change that over and figure out how many per second. Okay, our time in this one was 1 second if we wanted to think about it strictly with the formula, but following through with the logic and how that thinks through, I think is a little bit better for this problem. So if we want to look then at the linear speed of the belt, okay, we're thinking about these things. We've just found omega. And we know our radius. Just found omega. And we know our radius. Our radius is 6. So when we multiply this out, what we're going to get is we're going to get 16 pi centimeters per second. If you needed to get a number for that, if you needed to get an actual decimal form, you could just take 16 times 3.14 if you had a truly dumb calculator, and that would give you a close enough number to help you if you needed to. But leaving things in terms of pi is really right where we are right now, and I want you thinking in terms of pi. So let's just make sure that you're able to leave your answer in terms of pi. Okay. All right, another thing we're going to think about is satellites. Okay, so a couple people that have overlap with physics might find that we're thinking about the same concept that we did in physics, but with formulas that do the same thing, but might be coming at it from a different angle. So we've got a satellite that's traveling in a circular orbit around the Earth. The green is the Earth. There's a satellite up here on the blue circle. So we've got this whole thing happening. The radius of the Earth is 6,400 kilometers, and then the distance to the satellite is 1,600. Yes, way, way, way out of proportion here. But I needed to do that so you could see it and I wouldn't take up too much of the page. So you've got this happening. And so this is kilometers, and it takes 2 hours to go around the Earth once. So we want to find the linear speed in kilometers per hour. So we have a radius, and we know the time that it takes to go around one orbit. We have our radius, but we have to be careful that we take into account that it comes from the center of the Earth and then adds the 1600. So we have our radius there. We have our theta. Remember, it's the of how far in radians. So when we go around one orbit is 2 pi. That's our theta, our radian measure for the angle that goes around. Our velocity, okay, velocity with the amount of things that we have theta, and we have our time, we have our hours. So we want to use the one that uses r and theta time. And our time is 2. In pi kilometers per hour. Get practical. Times pi times pi. And so we get 25. About 25,000. We could do this with a regular old dumb calculator. 1,000 pi. Whoopsies. Make that so big. Times, we could do 3.14. You could just do pi here. 3.14. 25,020. Even if you did that, you could use about 25,000. I did a little creative rounding there because really the circumference or the radius of the Earth is kind of not exactly that, but it's close. So we're in the neighborhood of 25,000 kilometers per hour. But 8,000 pi is good. We only have really just one decimal place of accuracy anyway, so, or 2 in these, so rounding to 2 digits is appropriate. Here, that's a whole different lecture, and if you gave out the whole to 25,120, I would also say that's fine. So about how far does it travel in 4.5 hours? Well, we take our rate times time. If we think back to distance equals rate times time, if we're thinking about these formulas, our v equals s over t, which in essence does end up taking our rate times our time. It gives us 36,000 pi, or about 110,000 kilometers would be the distance that satellite travels to go around the Earth. Now they get a lot more precise, obviously. For the GPS systems and those things, they have to be way more precise than being 120 kilometers off. Or however much that comes, they have to use much more precise numbers. But it still all works out. That's all I have for you today. We'll have those graded for you shortly. I do need to review your answers and get them back to you. I'll be releasing the grades a little bit later, and I know I had sent instructions out on that. I'll send them again, but for those that like to hear instructions, when you receive your grade report, you'll get one for section 1 of your quiz and one for section 2 of your quiz. Those 2 grades will be combined to make the grade that you'll see on GradeLink. And you'll be able to view any comments that I've made on your quiz. When you receive it on a laptop, you'll see a little view button. And on the majority of phones, you'll see a little view link that you can click on to see your feedback. However, there are some phones that when you receive it, it appears that they don't give you a way to view your quiz. However, for whatever reason the Google Docs doesn't show up right on every phone as far as seeing where you can click that view button, but if you click around in the white space underneath where it gives you your score, the view button's there. It's just that the word doesn't show up, and you click around a little bit, you'll find it, and then you'll be able to view your results. Okay, so that's it. That's all I've got for you today. I hope you have a fantastic day and find some joy, find some time to relax a little bit, and God bless you.